Let's talk about EMI. I know, Amelia. Way to start off a chalk talk on a bummer. I get it. EMI is a pain. It can cause all sorts of problems in electronic systems. And no, we can't get rid of it completely, but we can reduce it. And one way we can do that is with the choice of power inductors we use. But not just any power inductors, the Vishay IHLE high current inductors. Hi, I'm Amelia Dalton, host of Chalk Talk. EMI mitigation is an important design concern for a lot of different electronic system designs. In this episode of Chalk Talk, Tim Shafer from Vishay and I explore how Vishay's IHLE power inductors can reduce radiated EMI. We also examine how the composition of these inductors can support the mitigation of EMI and how you can get started using Vishay's IHLE high current inductors in your next design. And before we get started, don't forget to click that link. There you can find even more information about this topic from Vishay. Hi, Tim. Thank you so much for joining me.
Hi, Amelia. Nice to be with you again.
Excellent. Okay, so Tim, last time we talked about the IHLP power inductor and power inductors in general. But first, can you give us a brief overview of what we talked about before?
Sure, Amelia. Brief overview of the power inductors, again, will help us clarify our goal on how to use the IHLE product to reduce radiated EMI. So recapping, last time we learned that a power inductor typically is used for currents greater than 1 amp. And the applications for power inductors include energy storage for DC to DC converters, and that can be your boost, your buck, or your SEPIC converters, which are called buck boost converters most of the time. And then they're also used for high current noise filtering. And this might be in DC motors, speed controls, or anything with a pulse width modulation control that would have sharp voltage peaks. And maybe that would be a LED brightness control that puts noise on the line. And we're going to be talking about that type of noise a little bit later. Now, the power inductors are available in through-hole, surface mount, and other types of terminations. They're available in what's called shielded and unshielded configurations and many, many different construction types, which a few are shown here on the screen. So what's the difference with the IHLP? That's what we talked about last time. Well, many of the inductors are made by winding insulated wire on a core of magnetic material, like you see here on the photos. But the IHLP inductors, if you remember, are different. They basically are made backwards. The IHLP starts with a coil of wire, and then the magnetic material is formed around the outside of the coil, which you can see here. And you can also see in the cross section that the powdered iron completely surrounds the coil. Now that's going to be good for EMI. This provides other advantages as well as far as performance, size, and durability. Also, they're very temperature stable. Some of the inductors vary over temperature. The IHLP does not. They have very high saturation currents, which means that they can handle high DC currents without changing inductance significantly. They have low losses. So when you put them in the circuit, they don't contribute to the losses as much as other types of inductors do. And they have excellent shock and vibration resistance, exceeding all of the AEC Q200 automotive requirements that are so important.
Okay, so thanks for that review, Tim. But today we're going to focus on EMI reduction, right? So, what exactly is EMI anyway?
Well, that is a really good question. EMI is an abbreviation that stands for electromagnetic interference, and it is basically unwanted noise or interference that is in an electrical path or circuit. So EMI can cause electronics to operate inefficiently or behave erratically or stop working completely. Everyone has seen interference on their TV screen like shown here. That may happen when a vacuum cleaner is turned on or the blender is turned on and the screen tears. Well, that's EMI. That's electromagnetic interference. You also may have heard it on the radio. You turn on a hair dryer, you get static in the radio. That's EMI, or electromagnetic interference, and that's what we're going to try to get rid of. While this type of EMI is annoying, it can have much worse effects. EMI can cause failure of critical communication devices like GPS or other systems, other computing systems. So EMI must be controlled within limits that are established by the FCC, which is the Federal Communications Commission. And I'm reminded of a story or a situation that occurred where commercial airliners were on landing approaches to an airport in California. And on that approach, they experienced a glitch in their autopilot landing systems just a short distance from the runway. Now, not every plane experienced this every time it landed, but it was prevalent enough that it caused quite a bit of concern. So, after much investigation, it was found that an electronic cash register in a drugstore in the flight path was the culprit. If a register transaction was tendered when a plane landed on autopilot and it was directly overhead, the EMI generated by the cash register was enough to crash the autopilot software. Fortunately, no planes crashed, however.
That is scary, Tim. Now, how do we get rid of EMI?
Okay, well, first of all, we need to understand a little more about the EMI. So there's two types of EMI that we have to worry about. One is conducted EMI, which is transmitted through the electronic components and conductors on the PC board of the circuit. So the conducted EMI is typically caused by the switching noise in the MOSFET devices. As they turn on and off, they can create spikes which have high harmonics that cause the switching noise. So conducted EMI has different FCC limits than the radiated EMI that we'll talk about in a minute. So FCC limits are imposed on conducted EMI for up to 30 megahertz, and you actually have to test the circuit and stay within the EMI limits in order for it to get FCC certified. Now we're going to speak about radiated EMI. And radiated EMI is caused when the electronic component or a conductor on the PC board acts like an antenna that broadcasts the radiated EMI into the air. So radiated EMI can induce noise in nearby components or PCB traces. The radiated EMI can be very tricky and expensive to mitigate. And FCC limits are also opposed on the radiated EMI, and those go from 10 megahertz to 1 gigahertz, so much higher frequency and wider range. So here's a basic circuit diagram of a DC to DC converter. And you can see the two switches there, and they switch on and off and create the DC to DC converter voltage change so that that can be regulated and controlled for the load. So those switches, as they go on and off, they can cause the conducted noise in the line, and they can be transferred directly to the load. And that load might be a computer that might have a very sensitive microprocessor that could be upset by those EMI signals. So radiated EMI can also happen, and they're transferred through the air from the components to the load, or maybe even to the PC board or other components on the board.
Okay, so I can definitely see how EMI could be a problem. So, again, Tim, how do we get rid of it?
Well, the thing is that we can't get rid of it completely. We can only reduce it. And there are many methods to reduce the EMI. Some of them have to do with the printed circuit board layout, some of the circuit design in general, but we're going to focus on the power inductors because typically power inductors will have some of the highest current on the PC board running through them, so they can be an issue for EMI. So let's talk about the two different EMI fields again. So two EMI fields have to be considered for EMI reduction. And anytime you have current flowing through a conductor, which is shown in green here, a B field is produced, and that's shown in red. The B field is associated with magnetic flux. Now, inductors store energy in the B field or the magnetic flux, and that's what we want. That's what they're supposed to do. The B field can be well maintained within a good inductor like the IHLP. So the B field typically isn't a problem when using the IHLP. An E field is also produced when a voltage differential is created. This is what's called the electrostatic or electric field, or we're just going to call it the E field for short. So inductors radiate E fields. Now, they're just the opposite of capacitors because capacitors store energy in the E fields. But let's talk about the B fields in a little detail first. All right, we learned that anytime you have current in a conductor, a magnetic field is produced. And we see that here in the diagram. The B field is composed of the magnetic flux and is concentrated by a magnetic core material, which is shown here. If the inductor is not shielded, you can see that the B field escapes out into the air where it can affect other components, PCB traces, or the load. So this noise can definitely cause problems if it induces that noise into the traces or other components. Different inductor configurations control the B field to various degrees. So here we have the main types of inductor configurations. First of all, we have the drum inductor, and you can see that it has an open magnetic field, that the magnetic field sprays way outside of the inductor, somewhat similar to the inductor up in the corner that's just a rod inductor. So these are the noisiest. They not only have the B field going out in the air, they also have an E field that we have to deal with. But we'll talk about the E field a little bit later. Now we have the shielded drum inductor. So what they do is they take another piece of magnetic material and they put it around the outside, and that shields it somewhat. As you can see, it's much better than the drum inductor on the left, but there still is magnetic field that exits the inductor and goes out into the air. And then finally, we have the composite or the IHLP type inductor, and you can see that the magnetic field is enclosed completely within the IHLP. There's no way for it to get outside of the inductor like there is on the other types. So this does the best job of reducing the B field flux leakage. So just using this type of inductor can help reduce your conducted EMI significantly. So we've seen that along with a B field, an E field is also created. And once again, that's the electrostatic field, and it's created when a plus and minus voltage is present, as you can see here. And as we said, the capacitors store energy with an E field, but inductors will radiate E fields. You can see down below here, there's a scan, an E field scan. And in the very center, it's kind of difficult to see, but that is an inductor that is in the red shading. So you can see that the red shading very well defines the shape of the inductor. It's a rectangular shape on the PC board. So this is what we have to get rid of because this E field scan is very evident, and it's showing that the E field peak is at 10 to 110 megahertz. So the best way to stop an E field is with something called a Faraday cage. Now, this was named after Michael Faraday, who was a pioneer in electromagnetic theory. And the shield is composed of a special metal that shunts the E field to ground so it doesn't radiate out into the air. Well, the problem with Faraday shields is that they are very bulky and they're also expensive. You can see here where we're putting a Faraday shield on top of some components. So you can imagine the expense that's involved, and also it makes the circuit much larger.
So, Tim, the only way to stop an E field EMI is with a Faraday shield?
That is correct. But Vishay has a very unique and cost effective way to add an E shield to your PC board without the added expense and bulk. And that's where the IHLE comes to the rescue, because the IHLE is our standard IHLP with an integrated E shield. So the shield provides space-saving, radiated EMI reduction without sacrificing performance.
Okay, so give me an example of just how good this IHLE is.
Okay, I'd be glad to. Well, the IHLE can reduce radiated EMI by 21 dB or more. And for those of you that are not familiar with 21 dB, the dB is a logarithmic scale. So it's not just a factor of 21 times, it's 21 times with a factor of a log in there, which makes it a very significant reduction. So what we do, we take a standard IHLP that you can see here, and then we have a specially designed E shield that is designed to attenuate the E field in frequency ranges of 300 kilohertz out to 1 to 2 megahertz, which is pretty much the sweet spot for a lot of the EMI that's created. So we take that E-shield and we integrate it into the IHLP, as you can see here, and we have the IHLE. And now you can see that in cross section that the insulated copper wire is completely surrounded by the magnetic material. So that keeps the B field inside. And now we have most of the inductor completely surrounded by its own Faraday shield. And that Faraday shield is then attached to ground. And then that ends up reducing the E field significantly. So as I said, the IHLE and its integrated E-shield can reduce the EMI by up to 21 dB. And this E-shield only adds 0.3 millimeters to the profile of the IHLP. So certainly much less than the Faraday shields that we saw before. Now, the IHLE is available in 5 popular sizes, from 5 millimeters by 5 millimeters up to 13 by 13 millimeters. And we have the 17 by 17 millimeter coming soon. And then to add even further, IHLEs are polarity marked, which provides even more consistent EMI, especially with unipolar pulses that are typically seen in DC to DC converters. Going further, I'll give you some more examples of how well the IHLE works. This is a graph of several different inductors that were measured for their EMI field with a DC to DC converter operating at 500 kilohertz, 15 amps, with 12 volts in and 1.5 volts out. So you can see that the ferrite inductor was the absolute worst. It had the highest EMI at 0 centimeters, which is on the x-axis, and then the field strength is on the y-axis. So it had 20 millivolts of E field that were present at the very top of the inductor. Now, if you look at the IHLP, it was significantly improved. So much better. It went from 20 to about 5 just by using the IHLE at 0 centimeters. And then we look at the IHLE. So the IHLE basically took the noise from 20 down to about 1 millivolt of EMI. And you can see all the way across the bottom of the screen that the IHLE was certainly better than all of the other inductors.
Okay, so that's some impressive EMI reduction. But how do I know if I need an IHLE or if an IHLP will work just fine?
Well, that is a pretty good question, too. And most designers do not know until they actually measure the EMI. So that means that they have to build up the circuit and put it on a special test. And these tests are fairly expensive to run. So you don't want to do them as many times as you might. So we can use the IHLE as what I call EMI insurance. And as I said earlier, the IHLE uses the same base inductor as the IHLP. So if the designer thinks there might be radiated EMI problems, then the PC board can be laid out to accommodate the additional terminals for grounding the shield on the IHLE and then add those to the footprint of the IHLP. So you can see down below that we have the standard IHLP layout, and the IHLE just adds the extra 2 terminals. So if the initial EMI testing warrants that you have to have the IHLE, then the PCB is ready to go for the IHLE. But if the IHLP by itself is enough to satisfy the EMI concerns, then the PCB can be populated with the IHLP instead without changing the PC board and with a little less cost than the IHLE.
That makes sense. Now, this was a lot to take in today. Tim, can you recap your main points for me?
I sure can. Yes, I went through a lot of interesting information on EMI. So, first of all, the IHLE can be a valuable tool to help reduce radiated EMI. The IHLE can eliminate the need for costly, bulky Faraday shields. An IHLP can be populated in the same space as the IHLE, saving cost, and if the IHLE is not needed. The IHLE is currently available in 5 sizes, soon to be 6, and they'll range from 5 millimeters by 5 millimeters to 17 millimeters by 17 millimeters. The IHLE has the same stable, rugged performance of the IHLP and will also help mitigate the conducted EMI. And then some customers use the IHLE's extra two solder connections to provide additional shock and vibration resistance. And the IHLE can withstand shock and vibration of over 50 G, which makes it very good for any type of automotive application or any other application where there might be lots of shock or vibration occurring. So Vishay encourages designers to consider the IHLE on their next design to control radiated EMI and also conducted EMI. So that's pretty much my recap. I hope that answered your questions about how to use the IHLE to get rid of radiated EMI.
It certainly did. Thank you so much for joining me, Tim.
Well, thank you, Amelia. It's been a pleasure.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Vishay. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talks section of EE Journal. You can't miss it, it's right across the top. Or check out YouTube, youtube.com/EE Journal.